Everyone. So I'm going to present my work, a schedule randomization policy to mitigate timing attacks in wireless HART networks. This is a brief overview of my presentation. First, I want to discuss about what real-time cyber-physical system is. Then I want to discuss about industrial control system, which is a representative example of real-time cyber-physical system. Then I want to talk about wireless sensor networks in industrial control systems. Then I want to discuss about the system model we considered in this work, the drawbacks of existing wireless HART networks. Then I want to talk about the vulnerabilities in wireless HART network that leads to timing attacks in such networks. And this is the main motivation of this work. Then I want to discuss about the countermeasures which I proposed in this work, followed by experiments and results. Then I want to discuss about the future research scopes in this direction and then conclude my presentation. So, introduction. Cyber-physical systems, as we all know, cover a large spectrum of today's life. A large class of cyber-physical systems are associated with strict timing deadlines. They are more specifically known as real-time cyber-physical systems, such as the industrial control systems, smart grids, railway traction power systems, etc. Now, in a cyber-physical system, large number of sensors are deployed in the physical plant, and they collect the sensor data and send to the controllers. The controllers generate the control signals, which are then sent to the actuators to actuate the system. In case of real-time cyber-physical system, all these executions need to be done within a reasonable amount of time to guarantee safety of the system. So, industrial control system is a representative example of a real-time cyber-physical system. So this figure shows a typical industrial control system where we have sensors. The main components of a typical industrial control systems are the sensors, the gateway and the network manager, actuators, and wireless sensor network. So in case of industrial control plants, we have different types of sensors such as temperature sensor, flow sensor, pressure sensor, etc. The sensors generate data after a certain interval of time, and this data needs to be sent to the gateway where the controller resides. Now the controller runs the control algorithms to generate actuation signals, which are then sent to the actuators to actuate the system. Since industrial control systems are large-scale setups, so large-scale wireless sensor network forms the main communication framework in these systems. In case of industrial control systems, in each of these communications, that is from the sensor to the controller and from the controller to the actuator, needs to be executed within strict deadline or hard deadlines. Otherwise, the safety of the system cannot be guaranteed and normal operation of the system components get disrupted. Existing wireless sensor network standards that are used in industrial control systems are ZigBee, 6LoWPAN, WirelessHART, Bluetooth, Wi-Fi, etc. However, WirelessHART is found to be the most reliable and suitable wireless standard for real-time communication. The communication in WirelessHART network is time division multiple access based. So each communication is associated with time slots of 10 milliseconds. WirelessHART supports multiple channels, and WirelessHART also supports sending a packet via multiple routes. So it has support for channel and route diversity. Now our work. Our system model consists of a network graph G equals to VE with M channels, where V denotes the set of nodes and E denotes the set of edges. And we also have N end-to-end real-time flows, which is represented by a set F. So this is a network graph where we have two channels that are denoted by blue and green. A real-time flow in a WirelessHART network is defined using the following parameters. So Fi is a flow which can be denoted using SI, DI, PI, delta I, and RI, where SI is the source of the flow, DI is the destination of the flow, PI is the period of the flow, delta I is the deadline of the flow, and RI is the set of routes from the source node to the destination node. Now I want to give an example of a flow. So here F1 is a flow. F1 has its source at node A and destination at node B. With F1 occurs in the system with period 4. So basically here there is a schedule consisting of 8 time slots where flow F1 is generated after every 4 time slots. So it has a periodicity of 4. And it has a deadline of 3, which means when it is generated at the first beginning of the first time slot and at the beginning of the 5th time slot. So from its beginning of, so basically the release, from its release, it needs to be sent to the destination node within 3 time slots, where 3 is the deadline. So here we have over this 8 time slots, we have 2 instances of F1. One is released at the first time slot, other one is released at the 5th time slot. And the first release needs to be executed within the 3rd time slot, and the second release needs to be executed within the 7th time slot. And AC and CD are the routes of F1. So AC is scheduled using channel 1, so I have marked in blue, and CD is scheduled using channel 2, so I have marked this in green. Now there are a few constraints which we need to follow in order to schedule a real-time flow in a WirelessHART network. Firstly, there should not be any transmission conflict in the network. So, firstly, there should not be any transmission conflict in the network. So in this case, if we consider this graph, so no 2 senders can send to the same receiver in a time slot, which means A to C communication and B to C communication cannot occur in the same time slot. No sender can send to more than 1 receiver in a time slot, which means in this graph, C to D communication and C to E communication cannot occur in the same time slot. A node can either send or receive in a time slot, which means A to C communication and C to D communication cannot occur in the same time slot. No collision is allowed in the network, which means if we have 2 channels, say channel 1 and channel 2, then A to C communication and B to C communication cannot use the same channel in the same time slot. Preservation of flow sequences. So this is a flow with route A, C, D. So A to C must be scheduled before C to D is scheduled in the network. Preservation of deadlines of flows. So all the hops of a flow must be scheduled within its deadline, which means here A to C and C to D must be scheduled within deadline of F1. That is, here it's 3 time slots from its release. So a real-time schedule needs to follow these 4 constraints in a WirelessHART network. Now, this is an example schedule in a WirelessHART network. This is the network graph, and we have 2 flows, F1 and F2. We are showing here the schedule over 8 time slots. Since F1 has a period of 4 time slots, so we have 2 instances of F1. F2 has a period of 8 time slots, so we only have 1 instance of F2. Now here F1 is having deadline 3, so F1 needs, the first instance of F1 needs to be scheduled within the 3rd time slot, and the second instance of F1 needs to be scheduled within this 7th time slot. There are certain drawbacks in this schedule of a WirelessHART network. Firstly, the scheduling policy in a WirelessHART network is centralized. It is decided at the network manager during network initialization, and the same communication schedule is repeated over every hyperperiod, which is the LCM of the periods of all the flows in the network. As a result, the schedule becomes predictable in nature. So so as a result of this predictable behavior of the schedule, a malicious attacker in the network can target a specific victim device, a node as the victim device, and it can observe or it can eavesdrop the communication associated with that victim device over a certain period of time to predict the time slots in which that particular victim device communicates with its neighboring devices. After observing the schedule for a certain period of time, the attacker can launch timing attacks such as selective jamming attacks targeting specific transmissions. As a result of the selective jamming attack, the timely delivery of sensor data or actuation commands is disrupted, as a result of which the safety of the system is hampered and proper functioning of the system is completely disrupted. As a countermeasure to selective jamming attack or rather timing attack, we propose a schedule randomization strategy, the SlotSwapper. SlotSwapper consists of two phases: an offline schedule generation phase, which runs at the network manager, and an online schedule selection phase, which runs at each node in the network at every hyperperiod. Now, I explain the steps of the offline schedule generation phase with an example. So this is a network graph, and I consider a base schedule. So I start with a base schedule over 3 flows, F1, F2, and F3. And I consider 2 channels in this example. And all of the flows have period is equal to deadline. So in this schedule, let us consider any flow, say for example, flow F3. Now F3 has a period of 8 time slots, which means within this 8 time slots, I have only one instance of F3. Now F3 has 2 hops, 2 to 3 and 3 to 7. Now in this base schedule, 2 to 3 is scheduled in 4th time slot and 3 to 7 is scheduled in the 8th time slot. Now, we need to follow the flow sequences. As a result, 2 to 3 can be scheduled anywhere in the randomized schedules before 3 to 7 is scheduled in the 8th slot. So I consider the scheduling window of 1 to 7, that is the 7 time slots. And then I check for transmission conflicts, collisions, deadline preservation, and flow sequence preservation, which are the 4 constraints of a feasible schedule in a WirelessHART network within this scheduling window, slots 1 to 7. After doing all the checks, then I generate an eligible list of slot channel pairs depending on following the all the constraints of a feasible schedule. So the slot channel pairs which are marked in green are the eligible slot channel pair. Now this slot channel pair, that is slot 1 and channel 2, cannot be considered in the eligible slot channel pair, because if you see here, this is flow F2 and the second hop of F2 is scheduled here in the 3rd time slot. If I swap 2 to 3 with 4 to 5, I cannot preserve the flow sequences of this flow. So I cannot consider this slot channel pair. Similarly, if I consider slot 6 channel 1 in the schedule, I cannot consider this, because if I swap this slot with this particular slot, then 2 to 3 and 3 to 7 will be scheduled in the same slot but in different channel. But according to transmission conflicts, a node cannot send and receive at the same time in the same time slot. Hence, I cannot schedule this particular transmission in this particular slot channel pair. So from this eligible list of slot channel pair, I select a random slot channel pair. Let this randomly selected slot channel pair be, say, this slot 1, channel 1, where transmission 1 to 2 is scheduled. Now I swap the current slot with the randomly selected slot. I follow the same steps for each hop of all the flow instances in the base schedule to generate a modified schedule, which is a random feasible schedule. So this is a base schedule. After running SlotSwapper on this base schedule, I get this random feasible schedule after one run of schedule generator. So what we do is we run the offline schedule generator for a large number of times in the network manager to generate a set of feasible random schedules. And then the network devices which are there in our network, they have limited storage capacity. As a result, we cannot store a large number of schedules in all the network devices. So what we do is periodically we send a set of schedules to all the network devices and distribute the schedules. This way, all the nodes can maintain the randomness in the schedules. However, they can run different schedules in different time slots, and hence the attacker cannot predict the time slots of the schedules. We have an online schedule selection phase. So after the schedules are stored in each network device, all the network device needs to select and run the same schedule uniformly at random. So we stored a pseudo-random number generator, and we initialize the pseudo-random number generator with the same seed so that all the network devices can select the same random schedule uniformly at random independently without any communication between the nodes. We measured the uncertainty in the schedule using Kullback-Leibler divergence or KL divergence. Now, KL divergence is a very common metric used in data mining, natural language processing, etc. We used this Kullback-Leibler divergence as a security metric in this work to measure the divergence of the schedules generated by our algorithm with respect to a truly random algorithm. Now, in case of a truly random algorithm, it can generate all possible feasible schedules. However, our algorithm is not optimal. It is optimal under certain circumstances. So we need to give a measure that how far we are from a truly random algorithm. For this reason, we use this divergence. A divergence value of 0 means our algorithm is working identical to the truly random algorithm, and higher the value of divergence, which means we are far from the truly random algorithm. So lower the value of KL divergence, better is the solution. Here probability G ik equals to J and G bar ik equals to J are the probability mass functions of the jth flow occurring in the kth channel of the ith slot generated by our algorithm, the SlotSwapper, and the truly random algorithm, which is denoted by A bar C. We have also used prediction probability of slots to measure the security provided by the randomized schedule. So in prediction probability, we have observed a set of schedules, T-1 schedules we observed, and based on the observations of the T-1 schedule, we try to predict the communication in the Tth schedule. Here, OJIET is a discrete random variable denoting the observation of the jth flow in the ith slot over link E in the Tth hyperperiod, and prediction probability of alpha IT is probability of predicting the same in the Tth hyperperiod based on observations of the ith slot in the T-1 hyperperiods. We ran our experiment in a real test bed which is the Indriya test bed in NUS, where we have 74 Telos-B modes. However, we also wanted to check our randomization strategy on different random topologies, for which we also ran our experiments in simulator. We used Kuja simulator and we generated random topologies over 100 Timotskaya modes, and we varied the degrees of the nodes from 2 to 8. And we generated the flows between 10 to 40 with periods varying between 2 to the power 7 to 2 to the power 10 time slots, and we varied the number of hops between 2 to 8. These are the 3 random topologies on which we ran our experiments. So this is graph A, which is a sparsely connected graph, and this is graph C, which is the densely connected graph. This is the intermediate one. So the main objective of using this different topology is to see how our randomization strategy works when we increase the degree of the nodes, and as a result of which the number of conflicts in the network increases. So how the scope of randomization differs as we differ the degrees of the nodes. So these are the results we got when we ran our KL divergence on the three topologies. So we found that KL divergence, the characteristics of the graphs are similar in all the three topologies. However, the values of the divergence varied. In case of single channel, we found that the divergence values are minimum. As we increase the number of channels, the number of collisions increased, which increase the number, so which actually decreases the scope of randomization and increases the divergence values. Also, we observed that as we increase the number of flows from 10, 20, 30 to 40, so the KL divergence values increases. This is because as we increase the number of flows, the transmission conflicts increase, so the scope of randomization reduced. This is the mean KL divergence, which we ran on three different graphs. Red, blue, and green, they denote graph A, B, C respectively. And we varied utilization of the slots. So the pyramids denote utilization up to 30%. The circles denote utilization between 30 to 60%, and the star denotes the utilization between 60 to 90%. We found that in case of graph C, where we have a densely connected graph, we were not able to get any feasible schedule when we had a number of channels more than one, and for utilization between 60 to 90%. This is because when the network is heavily loaded, we have too many conflicts in the network, which restrict us from getting a feasible schedule. This is our experiment when we ran our experiments on when we ran prediction probability of slots. So we found that in the first hyperperiod, we had no observation. So in this case, both without randomization and with randomization, the prediction probability is 0. Now, without randomization, the same schedule is executed over each hyperperiod. As a result, from second hyperperiod onwards, we have prediction probability 1 without when we consider the schedules without randomization. However, when we consider the schedules with randomization, as we increase the number of channels, the prediction probability reduced. This is because as we increase the number of channels, the scope of randomization increased. And also because there are more slots to schedule a flow. And also, as we increase the number of channels, as we increase the observation period, we found that more diverse schedules are occurring in the observed schedules. So as a result, the prediction probability reduced. So I want to conclude my work by discussing the future research directions. So there are some future scopes of this work. So SlotSwapper only considered the network flows in industrial control systems without considering the control loops in the network. However, in an industrial control system, we have a controller in the loop. So we want to explore we want to integrate the control loops into our framework and see how our randomization can be tuned, how our randomization policy can be refined based on the stability of the system, based on the control performance. And also, SlotSwapper is a centralized approach. We want to explore solutions where we can come up with distributed randomization strategy, because periodically we had to broadcast the schedules in case of SlotSwapper, which involves huge consumption of energy. So we want to come up with solutions where we can avoid such energy consumptions. So I want to conclude my work. So first I introduced real-time cyber-physical systems and timing attacks in real-time cyber-physical systems, such as the industrial control systems. Then I presented the countermeasure, the SlotSwapper, to mitigate timing attacks. Then I presented two metrics, scale divergence and prediction probability of slots, to evaluate the performance of the proposed countermeasure. Then I presented the future scopes of the problem. These are the two publications we had from this work. And an extension of this work, as I discussed, the future direction. So basically the distributed schedule randomization with the control and the loop is we did the work. It's under review. So right now I cannot discuss much about that work. Yeah, thank you. Any questions?
Okay, audience, if you have any questions, you can unmute yourself, or if you cannot unmute yourself, you can raise your hand and I can help you. Okay, I have a question first.
Yeah, sure.
Yeah, and because in computer science research area, security always has a trend. Someone propose a attack method, another one propose a defense, and then someone proposed another attacking method to attack such a defense mechanism. So is it possible to propose another attacking method to compromise your defense mechanism?
Another countermeasure to
another attacking mechanism to compromise your defense mechanism.
Yeah.
Is it possible? And and maybe what kind of viewpoint we can start?
So you are telling if we can come up with another defense mechanism, which, so actually in case of real-time systems, yeah, you can come up with multiple defense mechanisms to timing attacks.
Yeah.
This is one method. Of course, you can come up with so as an extension of this work, I came up with another countermeasure where I have distributed schedule randomization policy, which is more energy efficient and which also considers the controller in the loop. But the main challenging part in this type of defense mechanism is you need to take care of the deadlines of the flows, and you need to follow all the constraints of a wireless network. And coming up with a countermeasure while satisfying all the defense mechanism is a bit challenging. So this is the first work in real-time wireless networks. This is the first countermeasure in real-time wireless networks where we used schedule randomization policy. So schedule randomization policy has been used in uniprocessor systems, multiprocessor systems, but not in real-time multi-channel network. So this is the first work. Of course, you can come up, but there are certain challenges which you need to consider when you are coming up with the countermeasures.
Okay. I have another question in terms of the graph. You show three graphs in one slide.
Yeah.
I don't know, 3 graphs. Yeah.
Yeah, this one.
Oh no.
Okay, this one.
Yeah, correct.
Yeah.
And from my understanding, the degree is to control the density of the graph, right?
It's to see how this randomization policy works as we increase the degree. So basically, degree means the number of incoming and outgoing nodes from a the number of incoming and outgoing edges from a node. So as you increase the number of incoming and outgoing edges from a node, so the transmission conflicts increases. So basically, when you schedule a particular flow in a network, you need to ensure the 4 constraints of a real-time schedule, which is like no 2 nodes can send at the same time to like no 2 nodes can use the same channel in a particular time slots. So these are there are 4 constraints which I discussed in the slides. So as you increase the degree of the nodes, this constraints restricts the extent of randomization. So the purpose of testing in different topology is to see how the randomization works as we, how much the randomization is affected when we use different types of nodes with varying number of ages, because the conflicts and this conflict will reduce the extent of randomization, and as a result we may not get better results, or we may not get the results as expected. So to see how much it scales, we ran it on 3 different topologies.
Okay, thank you. And any questions from audience? Okay. I have no more questions. And audience, do you have any questions? You can raise your hand or just unmute yourself and directly ask questions. Okay. And now, and thanks for Ankita's presentation. And now we're going to end our SLS talks session. And I believe some of your audience have the publications. And here our SLS talk is a platform to show your work and publicize your research efforts. And then if you are interested in our SLS platform, you can drop an email to our SLS, to our GSC club, and we will arrange SLS talk for you to present your work. Okay, so if you have any questions, you can send an email to Ankita. And Ankita, can you write down your email?
Sure. Yeah. Thanks, Gawe, for hosting the presentation.
Okay, thank you.
Yeah.
You're welcome.
Yeah.
Okay, so that's all. Bye.
Yeah, bye.